Okay, so we're continuing our look at this example. We have x prime equals x squared minus 3xy minus 4, and y prime equals xy plus x plus y squared. First thing we did was look for the equilibrium solutions, and we found the equilibrium solutions right here. So there was 4 of them: minus 2, 0, minus 1, 1, 2, 0, and 1 minus 1. Okay, and now the idea is that we want to try to linearize this differential equation around each of our equilibrium solutions. So we remember that we need our partial derivatives. Okay, and so let's go ahead and continue with our example now. And we want to linearize about the equilibria. All right, so now we need our partial derivatives. So just as a reminder, f of x was x squared minus 3xy minus 4, and g of xy is equal to xy plus y squared. So therefore, f sub x is equal to 2x minus 3y. F sub y is equal to minus 3x. I'm going to go ahead and write this in kind of an order here. G sub x is y. That's the partial derivative of g with respect to x. G with respect to y, it looks like it's going to be 2. Oh, wait a minute. I'm looking at the wrong thing. Where's my g? There it is. If I differentiate that with respect to y, I get x plus 2y. Very good. And now I plug in these into my equilibria. So for example, at minus 2, 0, what is our Jacobian matrix going to look like? So plugging these in, I get my matrix A is going to be minus 4 if I plug in minus 2 for that. And then if I plug in into f sub y, what do I get? Minus 2 times minus 3 is 6. 0 minus 2 if you plug in the rest. Okay, and so this turns out to be a sink. And I know that right away because it's actually a diagonal matrix, and so the eigenvalues are right along the diagonal. So if you have 2 negative eigenvalues, that corresponds to a sink. Good, so how about at minus 1, 1? If I take a look at my matrix there, I think I get minus 5, 3, 1, 1, but you can double check that. And so in this case, my trace is minus 4. My determinant is minus 5, minus 3, which is minus 8. And actually, I can stop there because on my Poincare classification diagram, that puts me down here. And so I get a saddle. Oop. So this is saying at negative 1, 1, we have a saddle. That's the classification of our equilibrium. Similarly, at 1 minus 1, if I plug everything in, I get 5 minus 3 minus 1 minus 1. So in this case, the trace is 4. Trace is 4, but the determinant is again minus 8, and so therefore we have another saddle. Good. And what's our last one? At 3, 0, we have a matrix that is 4 minus 6, 0, 2. And this is the source. Very good. And so now what we want to do is go back to our graph, which is here, right, and locate these things. So what we're saying is that this was a sink, right? This is a saddle. This is a source, and this was a saddle. Good. And so we're able to tell a lot from just those 4 classifications, right? Because the sink is going to attract most of our solutions, and so we might guess that a lot of our solutions are going to end up at the sink. So let's go back to our plot now and see if we see what we're supposed to see here. So again, let's see, at minus 2, 0, you have a sink. So that's okay, you can kind of see that there. Maybe I can do that here. All right, so I think I was able to get something that I can actually write on here. So this is our, that was our source, sink. Do you see how that's a sink there? This, on the other hand, is a source. And then we had two saddles. Here's a saddle, and there's a saddle. And in fact, you can kind of see where the saddles have their, if we were to linearize, maybe this is closer here, we see some vectors in there, right? And this is just local. These are just local vectors here. There's one, there's one, there's one, there's one maybe. Okay, and so we're now able to uncover everything about what's going on with this system of differential equations, because we see exactly what the areas are. So, for example, in this area, what's happening? All of our solutions are going to infinity. As soon as you get below the saddle line somewhere, you know, all these solutions are heading towards our sink. Right? It looks like these might be going around. They could go around. It's hard to know outside, you know, very far outside the range. Good. All right, but this is kind of the idea of what we do with nonlinear systems. So let's review what we did. The very first thing we did was to determine the equilibrium solutions. So we found these points right here, right? And then the second thing we did was to linearize around each of the equilibrium. And then we determined what kind of behavior to expect, right, based on the Poincaré classification diagram. Good. And that's what we do for a nonlinear system. I'm going to pause on this, clear out this example, and we'll start another example. All right, I'll be right back then. All right, so continuing, we have a predator-prey equation here. And question that's always asked, can you figure out which one is the predator and which one's the prey? Let's see, the population of the prey is going to decrease with interactions, right? So the X must be the prey and the Y must be the predator, because they increase with XY. Good. Okay, let's go ahead and run through our steps real fast. First one up is equilibrium solutions. So go ahead and pause the video here and see if you can find the equilibrium solutions for this differential equation. Okay, so what we should see is our system. I'm probably going to use the top one and say from this either x equals 0 or y equals 3 minus x. If x equals 0 in the first equation, then we get y times 1 minus y equals 0 in the second. Let me clean that up a little bit. So therefore y equals 0 or y equals 1. And so then so far our solutions are 0, 0 or 0, 1. Okay, our other set of solutions, if y equals 3 minus x, would be 3 minus x times 1 minus 3 minus x minus x equals 0. Okay, and so we get either 3 minus x or the second equation simplifies to minus, or 2x minus 2 equals 0. So then x equals 3, then y equals 0, or x equals 1, and then y equals 3 minus 1 is 2. Good. And so now I have how many different, or how many equilibria? 1, 2, 3, 4, right? Whoops, 3, 4. Okay, now we're going to linearize each of these, but I think I'm going to pause this and we'll do that in the next video.